So welcome everyone to this presentation that Paul Stockwell is going to be taking part of today. My name is Jo Shales and I am your host for today's webinar. Process Vision partners with engineers and managers in the energy industry to improve reliability and efficiency through innovative image processing technology. Our systems detect and alert on hydrate, wax, and contamination in pipelines, while providing expert guidance for effective removal. With real-time visibility into pipeline health, accurate video evidence, time and location stamped, and unique optical detection technology, Process Vision delivers peace of mind and reduces the risk of equipment failure or shutdowns. Your speaker, Paul Stockwell, has a long history of dewpoint measurement systems. In 1991, Paul created International Moisture Analyzers, IMA. From the outset, the company intended to have the ability to look at multi-species analysis, and Paul served on working parties for the National Physical Laboratory in the UK for the improvement of moisture measurement, providing dewpoint measurement training for a variety of techniques for measurement engineers. With 35 years of experience in oil and gas systems, Paul was instrumental in the introduction of laser absorption spectroscopy using tunable diode lasers for natural gas measurements, assisting in the development of the first TDL system for natural gas, which has now become the industry standard method for moisture measurement in natural gas. As managing director for 20 years, Paul has gained insight into the safety and cost impacts of processes and their problem areas. The development of LineView, a permanent monitor for gas-liquid separator efficiency, has revealed some surprises and shown that we still do not know everything about what is going on in gas systems and gas pipelines. In 2017, Paul led the demerger of IMA to form Process Vision. Paul is named inventor on 16 granted patents with 22 pending patents, and firmly believes that a thorough understanding gained through imaging can make a significant difference in the oil and gas industry. Please welcome Paul as he presents his presentation on Does API 14.1 allow NGLs to be exported for free?
Okay, thanks Jo. My experience, as Jo says, is with instrumentation and gas analysis systems generally. API 14.1 is, if you like, the bedrock of what we do. It's really describing what the sample system should do in order to present a representative gas sample to any gas analyzer, whether it's a gas chromatograph, GC for gas constituents, or any other form of analyzer really. And that process takes the gas from a high pressure down to a low pressure. So we've got to be really careful about making sure that we don't hit the hydrocarbon dew point as that pressure and the temperature drop as we get it from the pipeline to the analyzer. We all know the last thing you want to do with a gas analyzer is put liquids through it. You'll write it off, you'll damage it, it'll stop measuring for a while until it's serviced. So it's all about keeping the analyzer safe. Now we can see what's actually happening in the pipeline. There are some marked differences between what we're seeing and what the analyzers are telling us. And the more installations we do, the more we learn. So really this project was kicked off by a transmission system operator, and they said, look, we know contamination is getting into the pipework. When we pig the lines, we take contamination out, we have to deal with it and dispose of it, but it's getting in through the entry points of the system without tripping an alarm. And they challenged us really to develop a piece of kit that would detect contamination events when it happens. Once it gets into the network, who knows where it came from, which particular supplier it was, or was it a particular event, or is it a continuous thing? So up until now, they don't really have a good handle on what's happening with liquids and liquid carryover. So we do live stream video to the control room operator, and that's really useful for them to actually see what's going on in the pipeline, apart from all the flow and the pressure and level sensors that they have. But obviously we use image processing to trip the alarm, so we don't ask them to watch it 24/7, but if something happens, their attention is taken to the videos. So originally we thought, well, there's not going to be many benefits for gas processing side, the supply side. This is all going to be on the pipeline operators side. But actually, as time's gone on, we're now thinking that there's lots of benefits for TSOs, but actually the main benefit would be for the gas processing side. As Joe says, once the systems go in, we provide a lot of support about, okay, if we do see liquids either occasionally or permanently, well, what's the next step? What are the possible solutions to move forward? So there's a lot of support that goes in when these systems go in. And we put these systems in on trial systems or on temporary installations, on a portable system, if you like, just have a quick look-see, or on a more permanent system as well. If we look at it from a gas processing side, the supplier side, for instance, to begin with, there was a survey done by amine experts. It was a very large cohort, 400 cases of plant failures, amine plant failures. And each of those was costing somewhere between $250K to $250 million per case. So in these 400 cases, they came up with 3 main causes: corrosion, foaming, and product quality. And 2 of those are all to do with the quality of the gas that is coming in the front end of the gas processing plant. So when liquids come across as well, it contaminates the amine, it causes foaming and fouling, and those are the main sort of problems for gas processing guys. If we move on to the gas pipeline side, then we're looking at compressor failures in the main. And there was a survey done of 71 compressor failures. And the survey was done by HSE on natural gas compressors. And they requested details from both manufacturers and users and they asked them what their design life requirements were, and they said 5 years is what we want between servicing, but actually the survey found that it was only 1 year 20 days before there was a problem on the compressor. Now you can see on 100% of cases there was liquid ingress between the faces of the dry gas seal, so there's only a few microns between the static parts and the rotating parts. And if that is filled with liquid, then more heat is transferred, and the 2 parts touch and then start wearing, and that's the cause of the failure, really. As the name suggests, dry gas seal requires dry gas. So from a liquid carryover point of view on gas transportation systems, then certainly errors in physical measurement and flow and calorific value, we'll go into that in more detail. As a high cost of pigging and disposal of contaminants, it's notified as waste material once it comes out of a pipeline, needs to be disposed of. Liquids tend to pool in the low point of any network, and so that causes a high pressure drop. So that means the compressors need to work harder to get over that restriction, which of course costs money. And then corrosion, both internal and external, so different mechanisms. Internal is when we have contamination, either liquid or solid or this sludge at the bottom of the pipeline. Corrosion can happen underneath that. And then the external corrosion is when that material breaches the insulation joint on cathodic protection systems. So that means that the CP system is then compromised and external corrosion can take place. So obviously the last one is the risk of a power station. When liquids are fed to a power station, it causes a problem, and that's happened quite a few times. That power station will seek compensation from whoever it was who was delivering the gas to them. So what we have really is a camera on the pipeline. We we've not had to hot tap so far in any of the installations, and we normally have an isolation valve between us and the pipeline, and then there's a flange adapter to adapt from whatever flange type there is up to our standard flange here. And this is the camera can. It has a secondary containment vessel underneath in the lower part, and the upper part is electronics. And basically, all the videos I'm going to show you are, first of all, real world situations. They're not in test rigs, they're from real networks. And imagine yourself looking down from on top. So imagine yourself standing on top of the pipeline looking down, and the videos we're seeing are actually the pipe floor down here. So we will see liquids on the pipe floor, and we'll see mist in between the camera and the pipe floor as well. So really it helps TSOs reduce costs. That's what it's all about, and improve safety. There is 3 elements to what we're doing: the financial, the safety, and regulatory issues as well, and they all come into play in different ways. But basically, this gives the TSO the immediate evidence that they need in order to slam the valve or request the flow to be slowed if there is an event taking place. So normally there is a contract between the supplier and the pipeline company, and this is an example of one from the USA. This is on the quality page, where the same page as where it stipulates the moisture content, the CO2 content, H2S content, and so forth. And the wording is basically the gas shall be commercially free from free liquids, any other substance that might interfere with the merchantability of the gas or cause injury to or interference with proper operation of lines, meters, etc. So fairly clear, there should not be liquids in this gas. Now, from the standards point of view, API 14.1 and the equivalent ISO standard, it basically says this standard does not include sampling, multi-phase flow or supercritical fluids. So if we see liquids, then API 14.1 and all the gas measurements derived from any sample system cannot be relied upon. ISO goes into a little bit deeper as to why that is. Attempting to sample a wet natural gas flow introduces the possibility of extra unspecified uncertainties in the resulting flow composition analysis. Sampling a wet gas flow is outside the scope of this document. So whenever we see liquids in a pipeline, it's a non-compliance to these standards, really. So if we have a look at the first video here, this is back in 2019, and what we have here, again, this is the pipeline floor. This is a time-lapse video. You can see time clicking along here. If we have access to process data, we can overlay that. Pressure here is 63 bar. And you can see here that we've got liquid sort of crawling across this solid material, this grease-like solid material on the pipe floor. And this was our first indication of the mechanics involved in what's happening within a pipeline. So you can see a little bit of contamination coming in from the side here. That's traveling particularly slowly. It's about 2 inches an hour that's traveling at. So what's happening is the contamination is entering. It might be a liquid, a slurry, or in this case a sludge. But if it comes in as a liquid, then that rapid gas over the top is drawing off the lighter ends, the NGLs and whatnot, and leaving behind a more dense liquid. So the liquid turns to a slurry, which then turns to a sludge, which turns to a solid material that is then fixed on the pipe floor and continues to dry out. So that when the lines are pegged, you might well get dry material out, but the dry material has actually arrived through that mechanism. So this is as close as we can get to a dry natural gas flow. It's running about 30 miles an hour, left to right. On this particular installation, it was a 36-inch diameter pipe. We've got a scratch here and a weld splash or something there as well. So down the left-hand side is our, if you like, our housekeeping data, frame rate, temperatures of various things here. We can change the focus, We have a liquid lens in the system, and we can change the illumination as well. And then we've got a secondary containment vessel that contains the camera and the illumination system, and we monitor the pressure in that, just make sure there's no problem there. So this first one is compressor oil. There was a compressor using a lot of oil 8 miles upstream of where we were. What surprised us on this one is the shape. It's a worm-like structure for this dense like material or liquid. And then a little bit later on in the afternoon, we're now 10 o'clock in the morning, 11 o'clock in the morning. So these are time lapse. So this is now mist flow. You can hardly see those two features on the pipe floor. And then a little bit later on, for some reason, operationally, they stopped the flow momentarily. And then when we restarted, then we saw this distributed flow. So how a liquid travels down the pipeline is variable. It can travel as a mist flow. It can travel as this is a deep mist flow there, and that's returned to the beginning as well. It can travel as a mist flow or a stratified flow. And there's lots of different reasons why it should be one or the other. So just to give you an idea of real time, that's that same event now in real time. And you can see this liquid just slowly crawling along here. So the only reason this is traveling is because of friction with the gas that's going at about 30 miles an hour. Now, the gas is from left to right, but you can see there's a slight angle on this flow. If I let this run, it would try and climb the pipe wall. As I say, we're looking at the bottom of the pipe wall here. It would try and climb the pipe wall. It collapses and then falls back down again. So as I say, the really weird thing is the shape. We weren't expecting that kind of shape. So this one, this next one is NGLs. Again, not the sort of thing we were expecting. Same 36-inch pipeline. And this was a gas hub, actually, so we saw a variety of flows here. We were expecting more of a stream rather than these separate lines of condensation or condensate that was flowing. Down the right hand side we have a measurement scale, so you get an idea of the scale of things when they happen. And then this last one, we had this solid material just static in the pipeline for weeks and weeks, months and months and months. And then all of a sudden this happened, sudden onset of mist flow. This turned out to be a process failure. There was a heat exchanger that had a hole and let liquid straight into the gas pipeline. So this is a mist flow, and on this installation, it's very repeatable. It happens day in, day out, and you can see it's 4 o'clock in the morning here. We can see a pretty good view of the pipe floor here. You might have to turn your lights off actually to see this properly, but as the day goes on, now 8 o'clock, 9 o'clock in the morning, now we begin to see the mist flow. To a point where we can hardly see the pipe floor, and this was only a 30-inch pipe, so just over 2 feet away, and we can hardly see the pipe floor beyond us. So it's happening the wrong way round. Joe, if you remind me, if we've got time in questions, we'll explain why that is. But you might expect if a gas is close to its dew point at the night time, the temperature would drop and we hit the dew point and see a mist flow. Actually, this is happening the reverse way round. So again, bit of detective work to find out why. So this is an incident that happened around about 10 to 2 in the afternoon. A little bit of liquid flow here to begin with, and then full scale liquid flow across a full field of view. So this went on for a few hours actually before the TSO decided to stop the flow, had enough basically. But we were able to look at the flows, the dew points, the water dew point and the hydrocarbon dew point. So at 10 to 2, this blue line is where that incident started, around about now. There you go. And at that time, we didn't see any change on hydrocarbon dew point. So we're thinking, okay, well, it's not NGLs then, it must be glycol or compressor oil or something else, and it's not water either. So it doesn't look like water. It doesn't look like compressor oil. So, but as I say, a few hours later, they stopped the flow. And this is what we saw when they stopped the flow. That's liquid pooling in the low point here. These particles on the top turned out to be pyrophoric and radioactive. So it'll burst into flames when it meets oxygen, and it's radioactive. So pretty dangerous stuff, really. And these drops of liquid apart from the main pool as well. So they wanted to change the filters downstream of where we were. So they depressurized the line, and this is the time lapse once they depressurize the line. So you can see that those liquids are drying out. So hang on a minute, they're volatile. So it can't be glycol, it can't be compressor oil. It's got to be NGLs, really. And that drying process continued until we saw, this is the following day, this dry material now on the pipe wall. Now that's a permanent reminder now of that liquid event. And when this happens in the flow station, then we've just reduced the pipeline diameter. And it's a permanent reminder, as I say. So now the flow meters will permanently overread until this line is cleaned, or somebody goes in and cleans it out, really. So this is a liquid onset event from the image processing point of view. So this is one of the parameters we look at, and it's brightness. So the blue is the maximum brightness that we see returned to the camera, and the red is the minimum brightness. So when things are fairly clear and stable, the difference between the two is quite clear. And then when things happen, you can see things go all over the place. So what we're interested in is the difference between the max and min. Not necessarily interested in the absolute value. So this incident happened on the supply side at about 8:45 in the evening. Now 900 feet away or 300 meters away was another camera on the TSO side. So we had one system on the supply side, one system on the pipeline side, and we didn't see that until 1 o'clock in the morning. So it took that length of time to get 900 feet. So you can see that liquid is traveling quite slowly, but once it starts, it just keeps on coming. On this instance, we were involved, the TSO escalated this incident with the supplier, and we were involved in that meeting, and we were able to show them that actually on the supply side, it now dried out by this time. We could show them live video, even though on the TSO side, they were still seeing liquids at that time. So they decided actually on this instance to let it run for the next few hours to see what happens, and sure enough, it dried out on the TSO side as well. So from an impact from GC measurements really is that we've got to remember that the GC is measuring gas phase only. Any of those liquids we've just seen either in a mist flow or a stratified flow is not included in that measurement. And GCs are used mainly in the industry to calculate BTU, and of course that BTU measurement will be in error as well when there's a two-phase flow. So BTU, Wobbe index, hydrocarbon dew point will all be in error, and quite substantial error as well. And flow meters will also be in error. They tend to overread when they're wet gas, but of course they're overreading because they're actually reading with NGLs, which is quite a precious commodity. So in terms of financial loss, when we see a mist flow, which is quite often actually, in terms of the unmetered NGLs going through these systems, we've got two examples here. One is 100 million scuffs per day, 100 million standard cubic foot per day, and the other is 400 million scuffs per day. So 100 million scuffs is about the average size of a gas treatment plant in the US. And normal sort of operating pressure, 900 psi, 63 bar. If we say the liquid volume fraction is 0.1%, so what we're saying there is on the flow, 0.1% of the flow is liquid, 99.9 is gas. With the gas flows involved, it stacks up quite quickly. 10,000 gallons per day of liquid flow, 42,000 gallons per day on a 400 million scuffs per day plant. And in financial loss, if we look at, this is the average price for NGLs over the past 5 years, 2.8 million per year or 11.2 million per year. So certainly something that, you know, from a gas process point of view, we should be looking at in order to improve that situation. And as soon as these go in, we can usually improve the situation considerably without too much change, just a change of process conditions really, or balancing the flows between different trains to improve things. And then we can advise, you know, depending on what the residual is after that, we can advise on what the next steps could be to regain that revenue. But the impact, well, up till now, phase separator performance has simply not been monitored, which is kind of odd. You'd think, you know, you need some feedback on any process to make sure it works, but at the moment it's not monitored. And of course, glycol, which is one of the main things that when lines are pigged, glycol is one of the main things they find. That's not measured in any gas quality measurements. There's no gas phase element to that really. And then really the industry ignores gas processors, ignores liquids, but NGL and glycol loss, and then increased operational expenses for TSO as well. So from a gas processing point of view, if we've got something like this, a process camera in the line, either at the back end or the front end of gas processing, we've got a lot better confidence in gas processing conditions. So a lot of gas processors run under the design flow because of the risk of foaming. So with a camera in place, we can run just that little bit closer to the edge so we can increase production. And if knowing that if there is a problem, then we can react very quickly. We can add defoamer before the foaming event happens, and decrease the amount of defoamer that needs to be added and prevent a system shutdown. And then lower the cost of glycol loss and lower the loss of NGLs. So from gas transportation side, the kind of thing that they're looking at is better confidence in gas quality. So the gas analyzers are great. They give us if you like, an idea of what's going on. But now we can actually see what's going on in the pipeline. We understand it much better. We can stop pipeline contamination events, or if we, for any reason, they can't slam the valve for any reason, at least then they know who it was and when it was, and they can allocate those cleanup costs to whoever it was that contaminated the line. We've noticed that they're also using information from LineView to optimize pigging operations. Now, in some cases that's decreasing, in some cases that's increasing pigger operations, but at least if you know the level of contamination that's going in, then you can optimize those operations. And then lower compressor servicing costs. Certainly, there's one installation we know where they really sorted this out properly, and they saw a 50% drop in compressor servicing costs. National Grid in the UK have published what benefits they expect to see from LineView. They had a particular event at a power station where they did have to compensate the power station. That was nearly $1 million. Then there was also a single contamination that they needed to compensate. That was $360,000. And then 2 ongoing costs, sort of annual costs ongoing, costs of liquid removal and disposal, 121, and then compressor servicing about 343,000 per year. So quite big numbers that we're expecting to see in terms of benefits for TSOs. But then moving to net zero carbon, we're looking at SMR systems, and the contamination we're seeing in a lot of the natural gas flows that we're seeing would actually foul catalysts and shorten catalyst life. So we're very keen to talk to people who are operating SMR systems or thinking about operating SMR systems to basically convert methane or methane to hydrogen, and see what we can do to extend catalyst life. So that's it. Thank you very much. I'm happy to answer any questions.
So one of the questions, Paul, and that was a fantastic presentation, thank you very much. One of the questions that has popped up is, how do you keep the optics clean?
Yeah, that one, hang on. So that one, I've got a few spare slides here. So this is the setup of line view for a fixed system. We're just about to bring out a portable system actually that will help things on a temporary basis. But on a fixed system, what we've got is the line view on top there. Then we have this vertical space here, which is, if you like, a dead leg. And that's a cushion that means that we don't get, if there is contamination flying around in the pipeline down here, it doesn't tend to come up here. We've never seen contamination on the window, apart from one, where this valve was about 40 years old, and when they opened it, it flung contamination up to the window. But it's a camera, we saw it. So what happened was they closed the valve, took this off again, cleaned it, put it back on. Took about half an hour. That's the only contamination event we've seen, really.
And you mentioned earlier on in the presentation to give you a reminder about how you were surprised about the reverse of dew point at night flow and why it didn't plan out accordingly. Could you go into a bit more detail?
Yeah. Yeah, I guess really that goes back to my water dew point days, where it was quite common really to see this diurnal change. We might be way down at -40 and it might have a 5-degree increase during the day and then drop again, to -40 at night and then up again. That was always explained by the fact that the water vapor is in-gassing and out-gassing from the pipe wall and maybe any material on the pipe wall as well. So as the pipe heats up, that water vapor sort of moves away from the hot point, rather like when you put toast under the grill, one side gets brown, the other side gets soggy. Moisture always goes away from the heat. And so because it's coming out the walls, it's going into the gas, and we see it as a wetter dew point during the day and drier during the night. So when we see this mist flow that is getting worse during the day and better during the night, we're pretty certain that's an indication that what we're seeing is a volatile gas. Really, it's got to be NGL. So it's a really good indication to say, hello, we've got NGLs coming over. When you think about what's happening in the gas processing side, on the NGL recovery side, normally what's happening is the last thing they do once the gas is nice and dry is to lower the temperature of the gas to drop as much NGLs out as they possibly can. So if you think about a flowing gas, and the normal way to drop a temperature of a gas is to expand it, to drop the pressure. We've just created the precise environment where a very fine mist flow is created. And from a filtration or phase separation process, that's the most difficult type of flow to filter out, really. So we're kind of setting ourselves up for failure in what we're doing unless we've got very good phase separation at low temperature. We're going to see this mist flow. Sorry, I wavered off subject there a bit, Joe. So
what's the most surprising thing that you've seen while monitoring the pipelines?
Two things. One of the most surprising thing is the amount of mist flow that we're seeing, the amount of liquids that we're seeing. When we put these systems in, we thought 99.9% of the time we'll be seeing just dry gas, like that normal gas flow. But actually, we've seen mist flow more often than not, and stratified flow on occasions, usually at startup or shutdown or when the system's unstable. So just the sheer amount. But I guess one of the events that occurred, we thought when we saw it, we thought, what the heck's that? I wish I had it here actually. Was a vortex appeared in the pipeline at a particular flow rate. Our camera system was just downstream of a flow station that had the gas was turning 90 degrees into the header. So we were just downstream of that, and we think we just caught that flow rate just right to catch this vortex. It's just hung around for about half an hour, at that particular flow rate whilst they were flow ramping up, and then as soon as they increased the flow, it disappeared off. So yeah, that's the weirdest thing we've got. But we have got a checklist of welding rods and rags and this, that, and the other that we haven't seen yet.
Excellent. And just opening it up really to the attendees, if there's any further questions that you would like Paul to answer, and if they're long ones, then feel free to come off, unmute and ask him directly.
Okay, I guess not, unless there's anything coming through. I can't see chat, and I can't see anything that's going on apart from my two screens here. So
All the questions have been asked.
Okay, good stuff. So I think we're about on time, aren't we?
We are.
Good stuff.
So if there are no other further questions, and if there are, then please do feel free to reach out to Paul. I'm sure Katie will send over details of contacts so that you can reach him if you need to. But thank you very much for attending the webinar, and we look forward to hearing from you.
Thanks, everyone.